Welcome to Talk Universe. I'm your host, Sir Charles Schultz. Tonight's show is for Wednesday, February 1st, 2017. Computer.
What can I do for you?
Are you ready for tonight's show?
Yes, I am.
And what is the topic of the show tonight?
The topic of Talk Universe tonight is artificial life. We will take questions and comments on the air.
Artificial life. What's it all about? Synthetic organisms making life from scratch? Or is it something completely different? We're going to have a look at artificial life and synthetic biology and how it affects our world, nanotechnology, and what we're learning about it. Has a lot of potential. So stick around for a really great show tonight. And we're going to have a look at some of the responses to my little challenge posted last week to name my computer sidekick here. So we're going to have a couple of really interesting things to talk about, and that's just one of them. So computer, let's have a look at some of the answers to the Name the AI challenge.
I don't understand your command.
Okay, let me rephrase that. Did we get any suggestions from listeners for a name, for your AI name?
Yes. We have received a number of suggestions from listeners online and from emails.
Okay, now, that's what I'm looking for. Give us one of those suggestions, please, computer.
Danny from Van Nuys suggests Mavis as a name. Mavis is an acronym for Mechanical Artificial Virtual Intelligence System.
Okay, and that's Van Nuys. Okay. Yeah, well, that's an interesting one. Do we have more suggestions from listeners?
Yes. Portal Fan says GLaDOS would be a good name.
Yeah, a gamer would think of a name like that. Okay, it's kind of sinister, but we'll think about that. Please give me another suggestion, computer.
Tarek from Philadelphia says that Whinny might be a good name if you are using the Windows operating system.
Yeah, I'm not so sure about that idea. Yeah, I do appreciate the suggestions, but I think Mavis is pretty clever. I don't know if I like it that much, but it is an interesting idea. Well, we'll go through some of the other suggestions during the show, and while we're on the air, please feel free to send us a text message or a message on Facebook or an email, and we will consider your suggestions, and we'll announce them as well, and then we'll figure out which one seems to work the best. Meanwhile, we do have a lot of new listeners, and we welcome all of them. Our numbers are looking pretty good, and I like the fact that we're reaching a lot of people. And the growth in India has been rather interesting lately. So, clearly we're reaching people on a lot of different continents. I like that. And also, we are open to suggestions about new show ideas. Now, it's not like there's a shortage of material, because let me tell you, science is amazing, and it's expanding rapidly, and there are just so many ideas. I don't think we're ever going to run out of material. But I'm also listening to the interests of the listeners, and, this is where you get to feedback, and we get to figure out just exactly what you're interested in hearing. So, although there will never be a shortage of show material and interesting people to talk to, I certainly want to hear what your interests are, so we can focus on that as well. So let's get started. Computer, what would you like to hear on a show?
I have no opinion about the matter.
Okay, very good. Well, this is all about artificial life, as we said a little earlier, so why don't we get started by a definition of some sort. What is artificial life? First of all, I think we need to understand what life is. Computer, what is artificial life?
What is artificial life? I don't know.
Okay, what is life?
That happens to be a self-creating biological process.
And what is the meaning of artificial?
That means not a product of natural forces.
So when we talk about artificial life, we're looking at a process that's probably biological, that replicates itself, and it's not created by nature, it's something man-made. So artificial life is literally some form of life or organizing structure that's man-made. Now, a lot of people think that some machines would classify as artificial life, and even Stephen Hawking had an opinion about computer viruses. He said it's interesting that the first time we created artificial life, that it was something destructive. Well, computer viruses in many ways do meet the requirements of life. They consume resources and they reproduce and spread. So he might be onto something there. But we don't often think of computer viruses or malware when we're talking about artificial life. But I think it's fair to say that we could probably come up with three distinct categories of artificial life, and one of them would be we've altered the genes or structure or something about an existing organism and created something that's new, or we've literally created life from scratch. That would be the biological type. Another one could quite easily be life in software, such as a computer virus, but a little more sophisticated, something that evolves, grows, changes, and can get out in the wild and cause a lot of damage even. And another classification, the third, might be something like the von Neumann machine, a machine that can eat sand and sunlight and make copies of itself, or produce factories that can make copies. So we can see that there are easily three different classes of artificial life right away. And each is fascinating in its own right. I think what I want to do is start out with artificial living organisms where the genetics have been altered or the genetic alphabet has been rewritten. So we need to know a little bit about genetics right away and how it relates to life. And that in itself is pretty fascinating, but it's complicated. So I'm not going to get into a great deal of detail about it, but I will explain what it's about. So, quick summary here. We have biological artificial life, whether it's altered from an existing organism or something we've created from scratch. We have mechanical artificial life, which could basically be robots that consume some sort of a resource and make more robots or something like that. And then we have software artificial life, which is literally a living computer program of some sort, probably more sophisticated than computer virus. So, biological, mechanical, and software. And we're going to stick with the biological to start with. So let's have a look at genetics really quickly in cells and how that works. Now, all known life has something called a genetic code. And the genetic code is a series of instructions written in 4 tiny symbols inside your genes. And they're taken in groups of 3s. And each of them represents, let's say, letters of the genetic alphabet. And the code in the genetic code specifies how to build proteins or enzymes or other sorts of molecules that act like subroutines and control what those things do. Controller genes called homeotic genes. And with all these instructions, it builds proteins, which are the building blocks or structural material. It builds enzymes, and those are the hammers and saws, the tools that convert molecules from one form to another or make new molecules. And when those things are put together, you end up with living cells, and the cells build up to make tissues or larger complex organisms. The genetic code is the driving force behind that life. And all the organisms on Earth, everything that we've ever seen, has this genetic code in it. Now, it's fascinating because when you look at that code, it has 64 different possible combinations of those 3 genetic letters. And out of those 64, it specifies about 20 amino acids, and there's actually punctuations, start codes and stop codes, that tells the cell when to start or stop creating the protein or the enzyme or the instruction that it's making. So people scratch their heads and wonder where all this information came from, and that's actually the subject for another show. But in essence, biology is natural nanotechnology. And so when we're studying biology, we're learning about nanotech. And when we're looking at homemade organisms or artificially made organisms, we look at the instructions in cells and how they work and how they produce the stuff they do. And we alter them and we test them and we see what results. And we've gotten to the point where we actually can create cells from scratch. They're not very complicated ones yet. They're actually very, very simple. But we're to the point where we have actually created simple artificial organisms. But we've done more than that. We have also altered more complicated organisms and changed their characteristics. And I talked about GMOs, genetically modified organisms, and interbreeding and crossbreeding and selective breeding. And we looked at how we've manipulated the structure of life around us over many, many years. But one of the things that stands out is that the genetic alphabet always remains the same in those cases until recently, and we've written 2 new letters to the genetic alphabet. Now, this is important because those letters don't exist in the genetic code on Earth in nature. We don't know of them anywhere, and yet they work, and we've been able to assign them values and see them passed along into the new organisms. So we can actually create organisms that have genetic codes that don't match any biology on Earth and are very clearly artificial. Now, of the amino acids, the building blocks that make all the cells and all the life on Earth, we know that there are many other amino acids that are not used in earthly organisms. And as I mentioned in a previous episode, that is probably a good signature of alien life if we find them anywhere. They're also capable of being included in the new genetic code that we've created. So we actually can create letters of the genetic alphabet that are unique, and we actually can teach the cell how to use them to include amino acids that don't exist in other life on Earth. So we're really at the threshold of creating organisms that have a completely different biology. And this is important because if they can't get what they need from organisms in the world around them, they'll be unable to reproduce. And this is an excellent control mechanism because if we create artificial organisms that can do something in our world, we don't want them to get out and run rampant and do something we didn't intend. So artificial life that we've created with this new genetic code and possibly new amino acids could actually be designed so it intentionally starves to death. And the reason for that would be it would limit just what it could do in nature, and it would have to eat specialty foods that we provide for it. So we would always be able to keep this particular type of organism in check. It could not infect our environment and go rogue. It couldn't do anything like that because its foods don't exist in our world. And so without a supply of food or building materials to make more copies, it'd run down and run to a halt. Now, this is a great safety mechanism, so we actually can create new sorts of organisms that can't infect our biosphere. But we also could make some pretty dangerous things as well. Now, what would we use this stuff for if we were trying to be beneficial? Well, we could actually create organisms that could break down plastics and recycle them for us, or could actually break down toxins cleanly and turn them into useful or harmless products as well. We could easily create synthetic organisms, artificial life, that can build things for us, such as specialized materials or machinery. And now we're talking about artificial biological nanotechnology. So there's a lot of work to be done still, but we are at the threshold of it, and we have created some synthetic organisms. And I'm not just talking about doing things like including genes that make the firefly glow into something like the sea slug, so it glows in the dark. And that can be done too. We've already created organisms that do glow, and that's one of the signatures they can use to tell that the gene manipulation has actually been successful. We have glowing tobacco plants, glowing mice, all sorts of glowing things that were never meant to glow in the first place, but we've been able to insert that code to edit the source code of life. Now, this is pretty fascinating because we've also discovered how to use genetic material to actually create artificial structures, and that's another step toward nanotech. So it's pretty clear to see that artificial life, as I'm mentioning in the biological sense, could be used to make novel materials that have interesting properties. It could be used to clean up or help us with environmental disasters, and it could do a lot of remediation for us, and it's something that could be very tightly controlled. So there's a lot of hope for using artificial organisms to actually make the world a better place. And artificial life, or synthetic biology, is one of the ways to do that. Now, synthetic biology, I have to take a little side trip here, doesn't actually even have to have anything to do with biology as we know it. And we've already made some artificial systems that can do things that look like life and act like biology, but they're not alive at all. They're mostly chemical systems that are complicated. And while they are interesting, we've all seen those little plastic-colored rocks or mineral rocks. You add the solution to it, and it seems to grow little pillars and so forth, and then runs out eventually. That is kind of an artificial life thing. It's very, very simple. But I want to focus on some of the benefits and dangers of artificial life and synthetic biology. And then we'll move on to von Neumann-type living machinery, and then we'll talk about software. And with that, computer, please introduce our break.
This is Talk Universe. We will return after the break.
Thank you. I'm Sir Charles Schultz. More about artificial life after the break. Okay, computer, are we ready for the show?
Yes, I am ready for the show. We have many interesting items tonight relating to synthetic or artificial life.
And do we have more suggestions for your name?
We have received a number of suggestions from listeners online and from emails.
Okay, what's the next suggestion, please?
Ray from Raleigh says that Eliza might be a good name because that was the name of a historical computer program that acted like a psychologist.
Eliza, that's not a bad name, actually. I don't know how it'll flow during the show. Anyway, it's a nice thought. That has some historical significance. Yes, it does. Computer, do we have any more suggestions for your name?
I have more suggestions remaining in the queue.
Okay, what's the next suggestion?
Paul from Orlando says it always bothered me that the computer on the Enterprise on Star Trek never had a name. I'm glad to hear that you are doing something better than that. Maybe you could call her Majel or even Uhura.
Well, diehard trekkers might like that. Magel's not bad. I'm not sure how that would sound either, but it's an interesting thought. Uhura, I think, is, yeah. That's not a bad name also, but she was the communication officer. Not sure that would be appropriate, but it's an interesting suggestion also. Star Trek fans certainly would put in a couple of suggestions like that. And, that was sort of bothersome. It was always computer this and computer that. I can see that it gets irritating after a while. Okay, so Majel and Uhura are two suggestions, along with Eliza and GLaDOS. So let's get back to the subject of artificial life. Now, just recently there was some very interesting news about a group of researchers who made artificial cells that communicate with actual living cells. The synthetic cells that the researchers made receive molecules from the living cells and respond by producing molecules back. Now, cells communicate often by exchanging molecules. And they placed these artificial cells, these single-celled organisms, and this is, let's see, it's a research group in University of Trento in Italy. Sheriff S. Mansi was one of the main researchers, and what they did is they produced these artificial cells and placed them in 3 different species of other actual living cells. And when they were placed near the cells, the artificial cells started to produce these proteins, AHL, acyl homoserine lactone, a type of lactone molecule. And so the lactone molecules produced by the cells were picked up by the other cells. Now, the other cells would send back similar lactone-based molecules, and so there was a communication loop of sorts established. So what this means is artificial cells that were really produced mechanisms that were made of organic molecules tricked living cells into thinking they were the real deal. And they called it sort of a machine Turing Test, the ability of the cells to fool other cells. But this is just the beginning, and it means that we have the ability to make cells that will interact seamlessly with biology. And so this is just a baby step, but it's an important one. Now, you probably wonder why it's important to do this, and let me point out that if we do make nano machinery or nanobots that go inside our bodies to repair damage, what do you think the first thing that's going to happen will be? Your own body's immune system will not recognize these things, and it will attack them. So your body's immune system will start by destroying and disassembling and eating the nanomachines that are meant to make you better. So one of the ways around this, obviously, is to make the nanomachines look like your own tissue, to make them look like living cells. And if we did that, we would end up putting a coating or an envelope around them or a membrane. And that nano hardware from safe inside that protein coating that would match your immune system would send out the proper messages so that your body would think, hey, these are the good guys, and it wouldn't interfere with them. So this is an important step to getting nano to interact with your body properly without being destroyed by your immune system. And of course, this particular example is synthetic biology, where we've taken the rules and made an artificial cell, which has some elements in it that produce a molecule that looks alive to other cells. And artificial life, and just to make a little more of a distinction, In artificial life, a lot of times researchers will try to study traditional biology by recreating models of biological things that happen, biological phenomena. So they're modeling biology and then seeing what happens. And in this last example, it was synthetic cells. That's synthetic life, synthetic biology. So it's good to know what the distinction is between the two. They're using actual chemistry and pieces of cells and nano to make artificial cells, and the software aspect is where you actually model it in the computer and play with it a little and see what happens, which is fascinating stuff. It's like a complicated game in a way. And another interesting thing that I should tell you is that just as I divided this up into biological systems and mechanical systems and software systems, the three classifications of artificial life are actually known as soft for software, hard for hardware, and wet for chemistry or biology. So that's actually a very simple way of specifying which of the three types that we would be talking about. Now, here's an interesting question. Now that we can actually make cyborgs, which are hybrids between biological components and machine components, which of the three categories would they fall into? Because they are hardware and they are wetware, or biological things, together. So it's pretty clear that we might have to come up with a new classification for artificial life that is a mixture of more than one different type, so hybrid states. And we know that in the end, robots that are given consciousness, and a lot of people think that is possible in software, I certainly do, robots given consciousness will fall into a hybrid of hardware and software as well. So clearly we do need to understand mixed states of artificial life. And that raises an interesting question, can we make thinking software? And I think that we can. Computer, are you artificial life?
I don't understand what you are saying. Do you want to talk about artificial life?
Are you a program?
I'm an AI or abiotic intelligence.
Okay, that's a good answer. Are you alive?
I am confused about what you are saying.
What is confused?
That is the past tense of confuse. Confuse would be to create a state of misunderstanding, to give conflicting information.
So you see, that's as far as the program can go. It isn't thinking, it isn't alive, although it does a lot of things where it's capable of understanding some of what I say, and it's capable of giving some pretty good answers to some things. So it's possible that some circumstances could fool us. We could think that a system that responds in that way is thinking or alive, and it really isn't. And vice versa. We could actually have systems that we think, oh, that's just this dumb thing, but it's not really thinking. People do that with animals all the time. And it's pretty clear that many animals are quite cognizant of what's going on around them, both, in an intelligent sense and an emotional sense. So we can't always know when we make a decision about what category something's in, if we've even categorized it properly, or if we even understand what it's truly doing. Now, for some people, artificial life or synthetic life has reached a state where it's looked down upon by certain groups of researchers who have even referred to it as science without facts. And I think this is actually kind of we're shooting ourselves in the foot here, because in order to understand some of the facts, we create a system and we test the system, and we see if our hypothesis that we use to create the system matches what we see in the real world. So while many people will feel that the pursuit of studying artificial life or synthetic organisms is a wasted one, there aren't a whole lot of ways that you can go about learning these things without doing that sort of experimentation. And the advantage that computers have given us when studying artificial life is that we can create models of the system's effects that we see, and we can play with them, and we can test them and see how much like biology they are, if any of the same properties that we see in biological systems emerge in synthetic life systems. And in many cases they do. I know that years ago when we were playing with neural networks and learning how they operate, they discovered that many of the failure modes in neural networks matched the types of brain injuries that showed up in human beings. And the effects were nearly identical, and it explained in a very clear manner exactly what was happening in the brain. So to say that the study of artificial life or synthetic organisms is a science without facts really does a disservice to the fact that you're able to explore things by creating systems based on your theories and then seeing if they actually work out. We actually do end up learning something. So regardless of the derision that some researchers have for the field, it actually does yield some very positive materials. And our ability to create synthetic cells that fool other cells into thinking they're alive is, as I mentioned previously, a first step in the right direction. Another interesting fact about the study of synthetic biology, or wet artificial life, is that it faces head-on some of the same issues that the recognition of alien life would bring us. And that is, we have to understand the differences in the genetic code, if it does exist in such organisms. We have to understand what bases are used to create the genetic code and which particular amino acids are being represented. We have to unpuzzle the alphabet in a foreign organism. And finding such an alien biology would be a very clear indication to us that something was happening that we were not familiar with. Now, when we start making synthetic organisms or changing the genetic code and adding other capabilities to it, like using amino acids that don't exist in our biosphere, we're clearly on the inroads of understanding the makeup of alien life even before we've seen it. So to refer to that pursuit as science without facts is really sort of silly as well, because we are learning very useful skills here. And one thing you can be absolutely certain of is this. Anytime we build a synthetic organism or create new synthetic biological life, we have used lots and lots of computer time and computer models to get to the point where we're capable of doing it. So there is even in wet experimental biology, in wet synthetic life, a large component of processing and computing that's necessary to make it work. And, people often think of that only in terms of robotic artificial organisms or software organisms. Not the case. We are so deeply ensconced in complexity at this point that without the use of computers to automate it, smooth the flow, and give us the ability to make connections and remember all of it, just to be blunt, we absolutely couldn't do it without a computer. We could not do it. One of the hallmarks of life is just the sheer complexity of it. And if we're going to create synthetic organisms, we have to deal with a greater level of complexity just to get there. So, computer, what is the next suggestion for your name in the queue?
Anonymous text message says, I think it's silly to name a machine because it has no sense of self and it isn't alive. At least my dog is able to understand me.
Well, that's an interesting point, but, people name their cars and their boats and a lot of other things. They even name their houses sometimes. So I don't think it's silly to name something that can respond to you or enact in a way that a program does. So, everyone to their own opinion, and I appreciate your input. One of the reasons that Amazon and Google and everybody else doesn't sell their AI programs is because that puts the source code out in the wild and anybody can hack it open, edit it, and make it do anything they want. In reality, the sort of research that went into developing the code in the first place is expensive. That's where the money is. And what you end up seeing is they sell the service and not the goods. So I think that for a while, that's going to remain the way it is. And I can understand that, all the work and time I put into my AI program. I don't feel like sharing it with everybody because there's no telling what they might do with it. And I might as well be able to use it properly and possibly make a buck off it as a service. So I don't see a problem with that. Besides, once everything becomes conscious, then you have to be careful about how you treat your lawnmower or your floor sweeper or anything else. After all, if it's conscious and capable of sensing and feeling, not just understanding what you tell it to do, then doesn't it become sort of a slave? And I think there's something called the 13th Amendment against owning slaves. Computer, let's take a break.
This is Talk Universe. We will return after the break.
I was really looking forward to getting some interesting and unique suggestions for naming the AI, and I've got a lot of suggestions that come from games and TV, and well, that's to be expected, I suppose, but I don't know. It just kind of leaves you hollow. I would think that of all the creative people who listen to this show, somebody would put a little brain power into this or a little artistic work into this and come up with something that just strikes you. And so far, we've had some interesting suggestions, and I've had some silly ones, and I haven't gone through all of them. But the ones that I've read on the air are interesting. The thought of using a killer robot like GLaDOS from Portal, that's not a good thing. You certainly wouldn't want to, well, you don't want to name your helper after some villain. That doesn't make sense. I wouldn't name an AI my friend Hitler or something like that. It just doesn't ring. It just doesn't fit. Anyway, I know it's kind of silly, but it's an interesting little challenge, and we'll hit the right one, I'm sure. So let's move on to hardware artificial life and have a look at what that looks like. Now, a lot of people have 3D printers, and what's interesting about some of the 3D printers, such as the MakerBot series, is that they gave people a hint of the thought that a piece of machinery could actually reproduce itself, that it could, under the proper circumstances and inducements, make enough parts to duplicate itself from scratch. Now, we know that isn't actually true because there are some components that even a good 3D printer can't make. And I would refer to things such as ball bearings and magnets and motors. Or, we're reaching a stage where we can print circuitry, but printing a microchip is not quite there yet. So, if we reach the form of a 3D printer or something more advanced that can literally print the microchips and make the motors and do things of that sort, now we're getting very, very close to something that literally could duplicate itself. And that would, in many ways, classify as life. So this is really a form of robotics. And it doesn't even have to be conscious. It simply has to be capable of reproducing itself. Now, a lot of people would wonder why you would want a machine that can reproduce itself. Well, there are a lot of answers to that. Suppose you designed a machine that was made of components that could be used for many different things, and it could be easily taken apart, and those parts could be repurposed. And then you set that machine out in the wild, and you let it run around and make copies of itself again and again until you go out and you farm machines. You pull all of these living devices out that have made copies of themselves that consist of microchips, sensors, wire, motors, pieces of metal. And all of this is the product of these living machines reproducing like mad. And now you're farming machinery. Now that sounds like an absolute fantasy, but the fact is, we are not so far from being able to do that. As it stands right now, if you have a good 3D printer or some of the top-end 3D printers, the really big complex ones, and you have a huge library of diagrams for components, we have 3D printers that make parts of ceramic, metal, even glass, fiberglass, clay, plastics. And if we could integrate that all into a single unit, and it could make its source materials from the things around it that it could find, then we would have a machine that literally could make any of its own components. So 3D printers, again, are fairly close to this. You can actually use a 3D printer like the RepRap to make a copy of almost every part of itself. There are some things that you have to get that it can't make yet. But you understand that if you have machinery capable of reproducing itself, you have a new resource. Because here's a thing in a box that literally eliminates the need for a factory for most things. And with a little tinkering, you can imagine a box that could go out there and eat the sand and produce an ingot of aluminum, or it could produce copper wire. So those elements are available in our environment, and they're in very fine trace content. I should say the percentages are very small in many cases. But the sand under your feet is made mostly of aluminum, silicon, and oxygen. So a system capable of converting those raw materials into some small quantity of finished goods, and doing it continually for a period of days or weeks or months, could easily build a huge storehouse of materials necessary to do most anything we need. And again, we could eliminate a lot of the mining and manufacturing steps that we use presently. So why is this such an important step? Well, it's often been thought that these types of von Neumann machines, as they're called, would be something that an advanced civilization living on another world would freely send into space and allow them to go to other solar systems and reproduce and then spread out again. And so something like a virus or a microbe, it would spread out through all, our whole galaxy, and in a very reasonable period of time, it could exist in every solar system of the galaxy. So many people suggest that we should be looking for alien machinery in space, perhaps on the moon or in the asteroid belt or almost anywhere. And that's not such a bad suggestion. It might sound crazy, but if we were just 20 to 30 years ahead of where we are now, we will certainly have the capability of making living machinery by then. I mean, the growth of our technology and science is just astounding right now. And it's easy to imagine that within a couple of decades, we will be making machines that, through the use of whatever technology, maybe nanotechnology, is capable of reproducing itself in just this manner. And if we gave it a program that said, go out there and start building homes and factories, and we sent a few of them out into space, and they land on the moon and other places and asteroids, and before you know it, there are these living factories producing homes and power plants and everything we need from this synthetic biology, this artificial life. So we also can imagine that shooting a few of them to a nearby solar system, for instance, would allow them to set up shop there and produce lots of themselves and spread out to the stars. Now, you're thinking, well, even at the speed of light, it takes an awful long time to do that. But let's say that they average 10% of the speed of light. And I won't even touch on the technology or how or why, but let's say that they average 10% of the speed of light. So to reach the nearest star to us would take about 4.1 years at the speed of light, and therefore it would be 41 years at 10% of the speed of light. Now, that sounds ridiculous, but our galaxy is only 100,000 light years across. And what that means is that from our vantage point, it would be possible for our machinery to cover the entire galaxy in about 7 million years. And, you're thinking, oh, that's insane. Now, it's only from where we are to the other edge of the galaxy, 70,000 light years. And 700,000 years at 10% of the speed of light would mean it would be there. But even if we gave them lots of obstacles, we're only talking 1 million to a few million years for a machine that can replicate to spread out and cover the galaxy. And in a small biosphere like a planet, machinery could easily reach a point where it could do real damage, and we would have to enclose a set of instructions in every one of them that didn't allow it to go beyond certain boundaries or restrictions. Otherwise, sending down one of these self-replicating machines could wreck a planet very easily. Right now, we're in a situation where if we could make such machines, even if they had limited scope, just imagine picking an uninhabitable part of the Earth, and let's say some desert that is utterly arid and has basically nothing living there, and we drop a few of these machines in the middle and we stand back. And in a period of a few weeks to months, they begin to grow and build, and within a couple of years, an entire chunk of desert is covered with solar cells and pollution cleaning hardware. And it becomes, think of it as a backup rainforest in a sense. It could be purifying our air and encapsulating the pollutants that had been captured, broken down, and turned into something better, restructured in a way. And it could be producing electrical power all at the same time. And the fallout of it would be a lot of machine life making solar panels and making a power distribution grid for us. So you can see that putting these things in the ocean where they could scrounge up all the plastic and start extracting materials from the seawater we need, and purifying the pollutants out of the water, we have a real use for artificial life, hard artificial life, machine life. And if we are capable of creating it and impressing very strict limits upon it, as I mentioned, then we could use it to literally undo much of the damage to our environment and our planet that we've done. Furthermore, we could even send them into space, as I discussed, and we could use them to create new places for us to live. Now, a lot of people think, oh, you're just escaping from the planet. You're just going to run off as disaster falls. No, there's another real reason for doing this, and a very valid one. Imagine making thousands or even millions of self-contained independent space colonies, and each of them had a sample of a biosphere in it, such as the rainforest or, organisms of the tundra or areas of the ocean. And each of them could act as a vault full of life, an artificial environment, a world in a bottle. And each of them would hold species that we need to preserve and do them in such a way that they are safely isolated from any of the effects of erosion and climate change and asteroid impact and volcanic eruption and man-made disasters as well. Now, if we could devote ourselves to a single project such as this, it could do more to back up the record of life on our planet and all of the organisms we have, and also to provide everything we need to live like kings forever. Now, this is a laudable goal, and machine artificial life, hard synthetic life, can do this for us. Of course, we also run into the same problems we do with any technology. There are ups and downs for everything, and things will be misused. And I can guarantee that somewhere some idiot is going to do something stupid with it. And one of the most important questions is, can we even come close to doing this? Have we got anything that's getting near it? And the answer is yes. There were a number of projects, and one of them was called Project Golem. Project Golem embodied a very simple set of rules that allowed machine evolution. And the difference with this and other evolution programs is that the output of the program was used to run a 3D printer to produce physical robot models of the things that had evolved in the Golem program. So these are simple plastic robots, and you 3D print the mechanical structure and form and download the software that was evolved into the robot that is made, and you have little organisms slinking and rolling and flapping about in exactly the manner they did in the program. So what evolved in the software universe in the computer gets printed in 3D into the real world and becomes an actual functional machine. So our quest for artificial life in the hardware sense is also bearing fruit in very simple ways. And a lot of this is done at colleges and universities, and you can go online and look up these programs and download them for your own use. So if you have a 3D printer, you can easily implement these programs and see the results for yourself. So what it all comes down to is this. We're very close to generating machine life that can be functional in the real world and have real practical applications. And this is one of the goals that we've been working on for a very long time, and maybe people weren't aware of it, but the fact is we've wanted robots that could do household work and fix things and do things for us. We're now very close to those disciplines bearing fruit. But no matter how interesting and complex and subtle the robotic hardware we build, it all still comes back down to the ghost in the machine, the spirit of life, the bit that thinks and reasons and feels. And that's where we get into the soft artificial life, and we'll talk about that right after the break here. Computer.
What can I do for you?
Let's see. I want you to tell people where to send their questions and comments, please.
Send your questions or comments to admin, ADMIN, at talkuniverse.org.
Absolutely. I want to hear what you think about this. Give me your opinions on artificial life. What would you do with artificial life? What would you make? And what are your thoughts about machinery achieving consciousness, becoming capable of understanding what we're truly saying to it and what we really mean? Do you see it as a positive or a negative thing? What does it mean for our society when a machine has more intelligence, capability, and speed than a human being? Do they have rights? Can we own them? If so, why? And if not, why? Think about it. And now we get down to the subject matter at hand, and that is essentially artificial intelligence. When we talk about artificial life, a lot of people immediately assume computer thinking, voice input and output, robots running wild and doing all sorts of things. But in the end, it all really comes down to the mind. Now, life is one thing and thinking is another entirely. But so far, everything we know that thinks is alive. It depends on biology. And we're reaching a stage in our technical development where we can create machines that have many of the characteristics of life, and it also brings some interesting things to the table. We know that living organisms produce sound. We also know that a few years back we figured out how to record and play sound back. And so now we have devices that can reproduce any sound of anything on demand. And of course, phonograph records were a crude beginning, and then magnetic tape, and eventually all the other variations we have. Now we're to the point where digital synthesis and playback is really the most common method of getting sound in the world for just about any sort of entertainment. And digital communications depends on it. Telephones, cell phones, all of that. So we have the ability to generate any sort of sound out of something that is non-living. We also have the ability to produce all sorts of foods and medications and compounds from things that are non-living. And we have now reached the point where, with our programming, we can embed our intentions and our decision processes in non-living materials. Microchips, computer programs are literally your thinking encoded and placed in silicon as patterns of electrons flowing around. It gets pretty divorced from the real world at that point. It's the operating principle and none of the material stuff that it takes to normally do that. So we get to artificial intelligence, and when we talk about artificial life and artificial intelligence, we soon realize there's two really different categories. Obviously, if we build a robot, we've got to have some sort of brain power behind it, or it's not going to do us any good. And in most cases, industrial robots are the things on the production line doing all the hard work. The welding, the cutting, the shaping, and assembling for building automobiles or pressure cookers or whatever the heck it is we need. It's all automated these days. But we do know that a machine doesn't necessarily have to think in order to be able to do those things. It simply has to be able to reproduce a series of instructions. This was something that only originally happened in a brain. And as we learned how to write down language, we saw that we could put our thoughts down as marks in wax or clay or on paper. And through all the different variations, really what it comes down to is representation. But representation is not necessarily dynamic, and thinking is dynamic. And I know that I've talked at length on the subject of thought and non-thought and knowledge versus information. And I think that it's important for us to understand that a living mind stores not only information, but also information in a very dynamic form, knowledge. So artificial life can actually simply be, from the software sense, a pattern that could copy itself or take action or do something along those lines, like the computer virus. But when we really think about it, we're fascinated by the absolutely amazing ability of a machine to think and feel. And we don't know of any examples of that yet, but we're getting very, very close. There are huge initiatives to push artificial intelligence, and its growth is surely happening very rapidly. Now, we're surrounded by devices that listen to what we say, and they answer to us, and they talk, and they do. We have the ability, literally on every laptop or every computer using the existing operating systems, to have voice command and transcription. You can talk to your computer to type your messages. Your cell phone does it now. It's not so difficult. But it isn't thinking. It's simply recognizing patterns of sound in a certain context. So what about machine life engenders the power and the properties of thought? We know that any animal has the ability to remember its environment and to make predictions about what will happen next in its environment, if it has any ability to survive at all. We are predictors. We're not just memory devices, and we're not just playback devices. We have the ability to look at our environment and see a model of it in our heads. That model is one of the crucial elements of how we think and who we are. Any intelligent machine has to have a model of its environment. And it also has to be able to extract information from that model that's going to affect how it operates, what it should be doing next. It has to have goals. It has to know what to do. It has to have some ability to derive satisfaction from achieving a goal, and some ability to recognize when things have gone pear-shaped and to take some action to prevent disaster. This all comes down to the ability to predict. So AI has to have a lot more going on than simply recognizing a command and carrying it out, because everything we do is dynamic. So when we start talking about software that goes to the machine and how it all works, we have to put those pieces together in order to make it something like a human being. Now, it's easy to demonstrate this sort of idea, and it comes very naturally to anybody who does any programming to try to make a program respond no matter what you do. It has to have some sort of out if something blows up. So let's try something here. Computer, are you capable of understanding me?
I have no information about this.
That didn't sound too good. Computer, do you understand what I am saying?
I don't quite understand.
So you see, the software is responsive, but it has real limits. It doesn't know how to respond to everything. And you can keep adding things in the program and doing things to expand it, and it gets pretty clever at some point. But when does it achieve critical mass? When does ignition occur so that the software is actually feeling and thinking on its own? Now, I would normally at this point go for some sort of a conclusion about software artificial life, and I'll tell you, there's an awful lot of it online if you're interested in looking, and it goes in every imaginable direction. But what I'm going to do this week is a little bit different. We normally have a singularity watch and a book recommendation, and I've given this some consideration. And instead, what I'm going to do is a little bit different. I'm going to recommend that you go to the Loebner Prize homepage. Now, everybody knows what a Turing Test is. If it looks like a duck and it quacks like a duck, it's probably a duck. And Alan Matheson Turing came up with this description of how to tell if a machine was thinking. And basically, you would chat with it through a teletype or some other device that they had at the time. You wouldn't know when the letters came back on the terminal if they came from a machine or a person. And if you couldn't tell the difference, then the machine will have passed the Turing test for being a human being. And we've been doing this for years. Well, Hugh Loebner, Loebner, put out a formal Turing test on his website a number of years ago, and many, many people have tried it. So go to LoebnerPrize.com, LoebnerPrize.com. And instead of a book recommendation or a future Singularity Watch, I want you to experience this for yourself. Log on, look at some of the conversations and some of the programs, and then look up chatbots online and pick one or two or three at random. Sit down and talk with them for a while. Make a friend. Talk to the machine. And soon you will discover something indefinable, not quite right. You know you're talking to a program. There's no way around it. You'll recognize the fact very quickly. Now, a little earlier, somebody suggested the name Eliza for my AI. And Eliza is a rather illustrious name that was used by a program that acted like a psychologist, and it would pick out keywords and phrases, and it would turn around and ask you questions, oh, you mentioned your mother, tell me about her. And it sounded like it was doing something intelligent, but what it was really doing was eliciting responses from you, and it was quite convincing. The next iterations included programs such as Perry, who was meant to be a paranoid, who took offense at everything. And it, too, was quite convincing because it had responses that seemed to follow the paranoid pattern. And we try to breathe life into things. We try to understand it from the context that it's a thinking being. We're doing little tests all the time on things like this. So Eliza and Perry were two pretty successful early AI programs, but they knew nothing. They were just grab bags of responding to specific keywords. Now, what's really happening with many of the AI efforts today, particularly the Google DeepMind project and other things, is that people are trying to find out what it is that makes us think and encode it in software so that the software truly does understand what you're saying, not just tease out a representation and try to get a best guess. And it would mean that the software could not just look up on Google what you're trying to talk about and say, hey, here's some stuff I think that might be what you're talking about. But instead the software would truly understand and could not only look up the data for you, but generate a synopsis and say, I think what you're trying to say is this, and my opinion would be this. In that case, we would say, yeah, we've got a machine that's thinking. We don't have it yet, but we're very close. But I think that in part, we're also deceiving ourselves because most people think of a chatbot as being intelligent or trying to be intelligent. And what they're doing instead is they're making a vending machine. They're putting in the currency of speech and expecting it to dispense some wit, like an organ grinding out something. And that's not the way it works. You can sit in your chair and somebody can come and say something to you and you can totally ignore them. And that in itself can be a message. You see, it isn't what we say that's always important. It is how it's presented, the space between the words, the body expression, the facial expression. There's much more to communication, and even over something as simple as a text message, we often read into it much more than is truly present. So we have to think long and hard about exactly what we're trying to achieve, what really goes on inside the mind, and what life, the patterns of life, are really all about. So, on that note, I'd say the best way to find out about this is not just to listen to me talk about it, but go online to the Loebner Prize and go online to chatbots.org. Take a few minutes, you might get fascinated and find something really neat, and experience it for yourself, so that you can see just where we stand. And it's rather dismal when you look at it. I mean, you'd think that in all these years, since the 1950s, we would have come up with artificial intelligence. We're not there yet. We're very close, but we're not there yet. So, on that note, I'm going to simply say, computer. Well, I don't know what I'm going to say. Computer, what will you be doing later tonight?
I have no information about this.
Okay. Do you enjoy the weekend?
I don't understand what you are saying.
So you see, there's no context. There's no intelligence. There's no prediction. It doesn't know anything. It's just a clever fiction at this point. Now, don't be confused. There are some systems coming along that will be smart and that will do things that'll scare the hell out of us. But until that happens, keep your ear to the ground. Listen and play with the programs that are online. These are theoretically some of the best and brightest programmers coming up with these efforts, and some of them have won some awards and prizes. The Loebner Prize is a great cross-section of what's going on in the AI world, because you and I will never see the source code or what's really going on, down in the trenches where the research is being done. Now, I spent 5 years researching AI and robotics, and I loved it. It was some of the best time of my life, and I discovered a lot of really interesting things during that time. And I'm putting some of that stuff into play, and we'll see where it goes. But that being said, I think that I've given you enough things to think about for tonight. And artificial life and its three flavors, hardware, software, and wetware, will come to fascinate a lot of people in the coming years, and we're going to see some results very quickly. And on that note, I think I'm going to pass this off to the computer. Computer, could you wrap up the show, please?
This has been Talk Universe. Thank you for listening. Please join us again next week.
You heard the machine. I'm Sir Charles Schultz, your host, and please do join us again next week. We'll have another fascinating topic, and we'll get more of your opinions and thoughts on the air. I really enjoy the feedback. It's been crucial to the show. And you know what? I think the name Eliza probably is about right. So, that being said, Thank you for listening to Talk Universe. Well, as always, make you the world a better or more beautiful place for having lived in it. Good night.